Hello friends, welcome to the session on sciences. Friends, as you know that from time to time we carry different lectures for you on different subjects, and today also through the live transmission of CEC we welcome you once again. Friends, we are having a series of lectures on band theory, and in the previous sessions we discussed a lot. Friends, carrying the series forward, today we are going to talk on one of the important topic, that is superconductivity, and for the discussion on the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor and she is teaching in one of the leading institutions of the country. So let's welcome our guest Dr. Sonia Bansal and let's try to understand what superconductivity is. Hello ma'am.
Thank you Geetika. Thank you Geetika. Dear students, we are talking about the band theory of solids, in which last time we discussed about the semiconductor. Last time we discussed about the semiconductors. What are the semiconductors? Where we define the less difference between the conduction band and the valence band. This time we discuss with the superconductivity. Means when we root the temperature of the material very low, then what happened? It means we just want to increase the conductivity. In the semiconductors, we deal with the conductivity of a material increases by lowering the band gap between the conduction band and the valence band. It was at the room temperature, but when the temperature becomes low, then what happened? Then again the resistivity of the material decreases. Where the resistivity of the material decreases, that phenomena is known as the superconductivity. In this case, the conductivity will increase. Now today's lecture we deal with the superconductivity. What are the superconductors? As we know that the Owens in 1911 explained the superconductivity. He was performing the experiment and on the properties of metal in journal, and it found that electrical conductivity, thereby the resistivity of the mercury. And then he observed that when the pure mercury is cooled, its resistivity vanished abruptly at 4.2 Kelvin temperature. Above this temperature, the resistivity is immeasurable, while below this temperature the resistivity is very small, that is essentially zero. It means resistivity drops of the mercury at temperature 4.2 Kelvin, and rho is in the order of 10 to the power 5 ohm centimeter. That is, at 4.2 Kelvin temperature, mercury is converted into a superconductor. This phenomena of losing resistivity absolutely to zero when cooled to sufficient low temperature. It means at 4.2 Kelvin, which is a very low temperature, the mercury resistivity loses, and then this phenomena is called as the superconductivity. There are the transition temperature or the critical temperature, which is very essential to define the superconductors. The temperature at which the transition of the normal conductor into a superconductor occurs is called as the transition temperature. It means this is that temperature at which the material converted into the superconductors. A normal conductor will convert it into the superconductors, and that this is also known as the critical temperature, and it is written by Tc. It means at this temperature, or we can say at the critical temperature, the materials behave as a superconductors. About the critical temperature, the substance is in the normal state, but below critical temperature, the substance is in the superconducting state. It means the critical temperature must be the highest temperature at which the material behave as a superconductor. For the semiconductors, we know that the critical temperature varies from 0.3 Kelvin to 1.25 Kelvin, and for the metals it varies from 0.35 Kelvin to 9.22 Kelvin, and for alloys the critical temperature varies from 18.1 Kelvin to 22.65 Kelvin. Now see here in this diagram we see that this is the temperature, which is 4.2, and this x side we have the resistivity and this side we have the temperature. Here we see at the temperature 4.20 the resistivity suddenly drops, and resistance of the mercury versus temperature graph represent that the resistivity decreases as the temperature becomes low. At the 4.20 Kelvin the resistivity of the mercury drops and it reaches absolutely zero. High temperature superconductors, that is HTS, high temperature superconductors, and abbreviated high critical temperature, are a family of superconducting materials containing copper oxide planes as a common structure feature. For this reason, the term is often used interchangeably with the cuprate superconductor. It means that the conductors which is in the family of the carbon oxide defined as the highest superconductors. The features allow some materials to support the superconductivity at temperature above the boiling point of the liquid nitrogen. Indeed, often the highest transition temperature of the superconductors. The ability of the use of the relatively inexpensive and easily handled liquid nitrogen as a coolant has increased the range of practical application of the superconductivity. Means by using the nitrogen we can make any material as a superconductor. So this is the one of the best example. Here we see that they are the chemicals, and at this temperature 90 degree and 80 degree they behave as a superconductors. Now see, superconductor. What is the definition of superconductor? What are the superconductors? Superconductors are the material having almost zero resistivity. As we know that the resistivity drops to zero, it means those materials whose resistivity becomes zero and behaves as a diamagnetic below the superconducting transiting temperature. It means temperature plays a important role. As the temperature decreases, the materials drops almost loses its resistivity, and its resistivity becomes zero, and this materials also behaves as a diamagnetic material. That is the condition for the superconductors. It means superconductors are the materials having almost zero resistivity and they are perfectly diamagnetic when the transition temperature when the transition temperature is very low. Superconductivity is a flow of electric current. This is a superconductor. Now what is superconductivity? Superconductivity is the flow of electric current without resistance in certain metal. As we know that the resistivity becomes zero, now the electric current will flow without resistance in certain materials, but at again absolute zero temperature. That's why we say that superconductivity is the flow of electric current without resistance in certain metals, alloys and the ceramics at temperature near absolute zero. And in some cases temperature hundreds of degree above absolute zero, which is must be minus 273 degree Kelvin. This is the man who discovered the superconductive materials and give the phenomena of superconductivity. That was the Dutch physicist, and his name is Ons. In 1911, superconductivity was discovered. Ons felt that the cold wire, what he was doing one experiment, and he explained this experiment as follows. Ons felt that a cold wire's resistance would dissipate. This suggested that there would be a steady decrease in electrical resistance. As a cold wire, the resistance dissipate, and he found that the materials its resistance, electrical resistance decreases, allowing for the better conduction of electricity, but again at the low temperature. In the next point, he explained at the some very low temperature, as we talking about the cold wire resistance. And here we see that at some very low temperature point, scientists felt that there would be a leveling of a resistance reached some ill-defined minimum value, allowing the current to flow with little or no resistance. When the temperature becomes low, the current to flow with the little, and there will be a no resistance. Then Ons passed a current through a very pure mercury wire and measured its resistance as a steadily lower temperature. which is much so surprised when he found that no resistance at 4.2 Kelvin. He found that when the temperature becomes very low, it is approximately 4.2, the resistivity of the material drops, approximately approaches to 0. Then he found that it behaves as a conductor, and then he gave this name as a superconductor. This was the experimental result. He observed as 4.2, the electrical resistance, opposition of a material to the flow of electric current through it vanished. Here see electrical resistance vanished. We see in the diagram, this is the temperature versus resistance graph. We see here that the temperature, as the temperature decreases, here we see we are cooling the material, the electric resistance will decrease, and opposition of the material to the flow of electric current. It means that extremely good conduction of electricity takes place, and that's name is superconductivity. What are the general properties of superconductors? If we talk about the electrical resistance, then we see that the virtually zero electrical resistance. We see that at the low temperature resistance drops, that it means all the superconductor must have a zero electrical resistance. Effect of impurities. When the impurities are added to the superconducting material, the conductivity is not lost, but the critical temperature is lowered. It means if we add some impurity in a pure metal, then it doesn't mean that the superconductivity will vanish, but it may be the critical temperature will change, at which the materials behaves as a superconductor. Effect of pressure and stress. Certain materials exhibits superconductivity when on increasing the pressure in the superconductors. The increase in stress result in the increase in critical temperature. It means when the stress will be applied to any material, maybe again the critical temperature will change, but the material behaves as a superconductor. Isotope effect, which is very important, where the critical or the transition temperature, that is TC, value of the superconductor is found to vary with its isotopic mass. It means superconducting state will vary according to the isotopic mass of a material. It affects the superconductivity of the material. When we talk about the isotopic mass, by applying the two different mass, then the critical temperature will change, but the material will behave as a superconductor. That is, the transition temperature is inversely proportional to the square root of the isotopic mass of single superconductor. The transition temperature depends upon the isotopic mass of the superconductor. Here we see Tc directly proportional to 1 by root of m. Now, magnetic field effect. How define that? What is the effect of superconductor? What the behavior of the superconductor in the magnetic field? If the strong magnetic field applied to a superconductor below its critical temperature, where it behaves as a superconductor, the superconductors undergoes a transition from the superconducting state to the normal state. More, we will deal with the more about the magnetic field effect. Here we see the Meissner effect that will define the magnetic field effect on the superconductor. We see the complete, you see the two diagrams. One temperature is above the critical temperature. Here in the next diagram we see that temperature less than the critical temperature. When the temperature greater than the critical temperature, here we see that the magnetic field of the material will pass through the material. Means here we see that the complete expulsion of all magnetic field by superconducting material is called the Meissner effect. Here we see this is the normal state. In this diagram where temperature is greater than the critical temperature, that is the normal state. It's not, material is not behaving as a superconductor. Now this is the superconducting state. Here we see that the expulsion of the magnetic field. Here we see no lines of magnetic lines of force pass through the material when the temperature is less than the critical temperature. Superconducting state when T less than critical temperature. The Meissner effect is a distinct characteristics of the superconducting from a normal perfect superconductor. Here we see these are the two differences of the material. When the material in the superconducting state, the magnetic lines of force expulsion takes place, but here when it is in a normal state, magnetic lines of force will pass through the material. As we know that if the temperature less than critical temperature, if it is a temperature above the critical temperature, the material again behaves as a normal temperature. Means superconducting material behaves as a normal material when the temperature is increased from the critical temperature. And then this in addition, this effect is exhibited by a superconducting materials only when the applied field is less than the critical field, that is the HC. Here we define the applied field also. It means it also depends upon the magnetic field which is applying to the material. Now we just discuss about the magnetic effect on the superconductors. Now we see if there is no magnetic field inside the superconductors. As we see in the superconductors, no magnetic field inside the material, that is expulsion of the magnetic field. Then what happened? Then the superconductor relative permeability or diamagnetic constant becomes 0. That means mu r is equal to 0. Then total magnetic field induction B is defined by if magnetic induction is equal to B. As we know that inside the material there is no magnetic field, so we can write B is equal to 0. Then we know that B is equal to mu naught H plus M. We put the value of B, which is equal, B is equal to 0, this 0 is equal to mu H plus M. Now M is equal to minus H, then M divided by H is equal to minus 1, and which is defined the susceptibility. It means the susceptibility of a material equal to negative unit, then we define as the materials behave as a perfect diamagnetic. Now see that magnetic flux quantizations, magnetic flux enclosed in the superconducting ring, integral multiples of fluxons, that will be defined by phi is equal to NH divided by 2E, or we can write it as N phi naught. Phi naught is the 2 into 10 power minus 15 Weber. Now effect of pressure. If the pressure increases, TC critical temperature increases. High critical temperature superconductors, high pressure. Thermal properties, as we know, the entropy and the specific heat decreases at critical temperature. It means in the superconductors, entropy of the material decreases or the specific heat decreases at the critical temperature. Disappearance of a thermal electric effect at critical temperature. It means superconductor doesn't show that the superconductor is not having the thermoelectric effect at the critical temperature. Thermal conductivity decreases at critical temperature. That define the types of the superconductors. Now here see Again we just come on the previous slide and we see here that the susceptibility is equal to -1. What it represent? It represent that the material is the perfectly diamagnetic. It means superconductors are perfectly diamagnetic materials. Now superconductor materials are at the low temperature, the materials behave as a superconductor. They are perfectly diamagnetic and they obey the Meissner effect. Then we can say the material is a superconductor. Now here we see the stress. If the stress increases, then dimensions increases. When the critical temperature increases, but it affects the magnetic field, that is Hc affected. What about the frequency? Frequency increases, zero resistance modified, critical temperature not affected. Impurities, magnetic properties affected. When we add the impurities, only the critical temperature will change when we add the impurities. Size, if the size less than 10⁻⁻⁴ cm, the superconducting state modified. And there are some general properties of the superconductors, that no change in the crystal structure. When we cool any material like mercury, its crystal structure will not change. No change in the elastic and photoelectric properties. When the material behaves as a superconductor, its elastic and photoelectric properties will remain. No change in the volume at critical temperature in the absence of magnetic field. If we remove the magnetic field, then the critical temperature will not change in case of the superconductors. What are the important features which define the superconducting state? Here we define the superconducting state by the three very important factors. Like, one is the critical temperature that we are discussing. Second is the critical field, that is the magnetic field applied, that is Hc, and the critical current density, that is the Jc. These three important factors define the superconducting state. Each of these parameters is very dependent on other two properties present. Here we see that in this diagram, here temperature, magnetic field, and the critical current density, and these all are very dependent on the other two. One depend upon the other, other depend upon the third, and these are dependent to each other. Now, critical temperature. What is the critical temperature? The temperature at which the material electrical resistivity drops to absolute zero. When the resistivity becomes zero, that temperature is known as the critical temperature, or we can say the transition temperature. Below critical temperature, material is said to be in the superconducting, and above it, the material behaves as a normal material. Below this temperature, the superconductors also exhibit a variety of several magnetic and electrical properties. When it is a superconductors, then its electrical and magnetic properties will change. Here we see the sum of the metals with its critical temperature. If we talk about the aluminum, its critical temperature is 1.2 Kelvin. It means aluminum behaves as a superconductor at 1.2 Kelvin temperature. Tin at 3.7 Kelvin. Mercury, already discussed that at 4.2 Kelvin, and it was the first discovered by the Ons. Niobium, that is the 9.3 Kelvin. Then tin, which tin plus this TiBa, copper oxide, will become superconductor at critical temperature of 125 Kelvin. Here we see again the electrical resistivity versus the temperature plot for the superconductors and the normal metal. Here we are doing the comparison between the normal metal and this is a superconductor. Now we see the electrical resistivity versus temperature graphs. In the normal metal, the resistivity decreases as the temperature, resistivity increases as the temperature increases. But here in case of the superconductor, we can see the electrical resistivity of the metal. Here we see that the resistivity of the normal metal decreases steadily as the temperature is decreased and reaches at low value at 0 Kelvin, or it is called the residual resistivity. Here we see that for the normal metal the resistivity is 0 at the 0 temperature, but here we see in case of the superconductors the resistivity suddenly drops at the becomes 0 at the temperature which is the critical temperature. Now we see that now the second definition is what is a critical magnetic field, HC. This is defined as the above this value of an externally applied magnetic field. As we define the Meissner effect, the magnetic field applied to the material, or we can say the magnetic field applied to the material which is cooled at a low temperature, then what happened? Then the superconductors becomes non-superconductor above the critical magnetic field. It means the critical magnetic field is the minimum magnetic field which is required to destroy the superconducting state, and that is known as the critical magnetic field. On the basis of that, we can differentiate the two different types of superconductors. Here we see in the diagram that this is the graph between the temperature and the external field. This is a superconducting state where the materials behaves as a superconductor. Up to here, that is the critical temperature. Above it, it behaves as a normal temperature. Thank you.
With this note, thank you, and thank you so very much for giving us this session. And friends, you are requested to be with us as we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on superconductivity, and for the discussion on the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor and she is teaching physics in a very leading institution, a reputed institution of the country. So let's welcome our guest Dr. Sonia Bansal and let's try to understand more about superconductivity.
Thank
Hello
you.
ma'am, welcome to the lecture.
We are discussing about the three factors which are required for the superconducting state. Number one is the critical temperature. Number two, which we are discussing, is the critical magnetic field. Again, I explained that what is the critical magnetic field. Here, just we see the definition first. This is the minimum magnetic field required to destroy the superconducting state. It means as the magnetic field increases, that the superconducting state will decreases. At particular magnetic field, the material behaves as a superconductors, and that magnetic field is known as the critical magnetic field and is defined by the Hc. It means above this value, above the critical magnetic field value, an externally applied magnetic field, a superconductor becomes a non-superconducting state. Here we see in the diagram that this is the superconducting state, and this is the temperature Tc, this is the critical temperature, and here this is the external applied field. About this field, the material behaves as a normal material, and below it the material behaves as a superconductor. The third point is the critical current density, which plays very important role to define the superconducting state. Now, on the basis of these, we define the type 1 and type 2 superconductor. It means the superconductors are of two types. Type 1, which is the soft superconductors, and type 2 are known as the hard superconductors. First, we discuss about the type 1. The soft superconductors are those which can tolerate impurities without affecting the superconducting properties. And in case of type 2, which is known as the hard superconductor, are those which cannot tolerate impurities, that is, impurities affects the superconducting properties. The soft, also called the soft superconductors, and these are also called the hard superconductors. Only one critical field exists for these superconductor, means for type 1 superconductors we have only the one critical field. For the type 2 superconductors, there are the two critical fields. One is Hc1 lower field, and second is the Hc2, which is the upper field. Now, critical field for the type 1 superconductors, the critical field value is very low in case of the soft superconductors, but in case of the hard superconductors, critical field value is very high. Type 1 superconductor exhibits perfect and complete Meissner effect. Type 2 superconductors do not exhibit perfect and the complete Meissner effect. In case of the type 1 superconductors, the current flows through the surface only. The current flows through the surface only in the type 1 superconductors, but in the type 2 superconductors, it is found that the current flows throughout the material, not only on the surface but throughout the material. These materials have limited technical applications because of very low field strength value, but here the type 2 materials have wider technology of very high field strength value, and these are the examples of the type 1, which is the mercury, zinc, etc. And here these are the combination of the two materials. We can say Nb3Ge, Nb3Si. We see by the pictorial representation the difference between the type 1 and type 2 superconductors. It means the one is a soft superconductor and this is a hard superconductor. As we already discussed that here we are having a one critical field, that is Hc. Below it materials behaves as a superconductors, or the material is in the superconducting state but at the critical temperature. And after that, after the critical field, the material behaves as a normal material, or it will be in a normal state. Now here type 2 superconductor, we see that here we are having a two critical field. One is HC1, second is HC2, where we see that HC1 is a minimum critical field and this is the highest critical field. Here we see that from 0 to HC1, the material behaves as a perfect superconductor. After that, magnetic field of line try to enter into the material, and the material soon coming into the mixed state. As a line of induction, magnetic field pass through the material. Now the material will come in the mixed state, and this is the mixed state where the material behaves as a superconductor as well as the normal material. But after this critical field, which is HC2, which is the highest critical field, the material behaves as a normal material, or it will be in the normal state. Now on the basis of that, we define that the two types of superconductors, first is the soft and second is the hard superconductors. Now what is a high critical temperature superconductors, low critical temperature superconductors and the high critical temperature superconductors? They are also divided into two parts. First is the low critical temperature superconductors, means those superconductors whose critical temperature is low. Here that superconductors whose critical temperature is high. First we discuss about the superconductors with the low critical temperature, then superconductors that require the liquid helium coolant are called the low temperature superconductors. In this type of superconductor, it is required only the liquid helium. But here in case of the high critical temperature superconductors, which are having the value critical temperature above the temperature of the liquid nitrogen, and it is called the high temperature superconductors, and the liquid helium temperature is about 4.2 at above the absolute 4.2 Kelvin above the absolute zero. Now we define the London equation. Basically London defined the superconducting state of a material. It defined the penetration of the magnetic field inside the superconductors, means it defined how the superconductors will become the normal material as the magnetic line of force try to enter into the material. On the basis of that, we define that according to the London theory, there are two types of electrons in the superconductor. It means the conducting state in a superconductor is because of the two types of electrons. One is the superelectron and second is the normal electrons. At 0 Kelvin, there are only super electrons, as the material behaves as a superconductor only because of these super electrons, as the temperature becomes at 0 Kelvin. With the increasing temperature, the super electrons decreases and the normal electron increases. It absolutely explains that the low temperature, the material behaves as a superconductor and its conductivity only because of the super electrons. Let us define as Nn, Un and Ns, Us are the number of density and the drift velocity of the normal electron and the super electron respectively. Means this Nn, Un define the number of density and drift velocity for the normal electron and for the normal electron, and here Ns and Us define for the super electrons. Now equation for the motion of, we all know that this is the equation of motion of the super electrons under the electric field is defined as m into dus by dt, which is equal to minus E. E is the charge and E is the applied field. Now current and the drift velocity are related as, we know that Is is equal to Ns E A US. Now we can define Js is equal to Ns E US. Here we can write US is equal to minus Js current density divided by number of electrons in the superconducting state. That is minus Js divided by NSE. Now we can take the differentiation of this and then we can put this value in this equation. US, this value of US we can put in this equation and then we can write it as d into minus Js divided by NSE divided by dt is equal to minus E. Then we can write it as Js by Jt is equal to minus Ne square E, which define the first London equation. Now London first equation gives the absence of resistance. Here we see in the above there is no concept of resistance, but here we define for the superconductor that the resistance will decreases at the critical temperature, but this equation doesn't have any term for the resistance. So London first equation gives the absence of resistance, that is E is equal to 0. Then we can say dJs by dt current density with respect to time becomes 0. We apply the Maxwell equation here on the electric field, and this is the magnetic field. We can write it as del cross E is equal to minus dB by dt, or we can write B is equal to del cross H. Then we put this value of B here. Del cross E is equal to minus d del cross A divided by dt. Now del cross E is equal to minus del into dA by dt, or we can write it as E is equal to minus dA by dt. Now in terms of current density we can write dJs by dt is equal to, we can write it as NS E square E by M, that we already defined. Then E is equal to dJs divided by dt. We take this E this side only. This is the E is equal to dJs by dt into M divided by NSE square. Here we see that all the time we are using the NS. NS means the current only because of the super electrons. Now again we solve it. dJs divided by dt into M divided by NSE square is equal to minus dA by dt. Now we can do differentiation of this, then finally we will get M by NSE square Js is equal to minus A. Now this is the Js is equal to minus NS E square by M into A, which represent the London's second equation. And we apply the Ampere law. We can write del cross B. Again here we don't have the resistance term. Now we apply the Ampere's law. We can write it as del cross B is equal to mu naught Js. Del cross B is equal to mu naught minus, here we put the value of Js from the previous equation, then we have minus NS E square by M into A. Taking the curl on both the side, that will be the del cross B is equal to mu naught minus NS E square by M del cross A. This is the formula to solve the above form, where we have del cross B, which is equal, we can write it as, the final term will be this. We can get del into B is equal to del square B, which is equal to mu naught minus NS E square by M, on we replace del cross A by the term B. Then we put it here B. We can write it as del cross A is equal to B. Now we can solve this equation as del into B is equal to del into del cross A. This all are from the gradient, and then we solve it, then its value will become 0. Now by putting this value in the previous equation, we will get, we'll put all the values in the previous equation. Now we are finally have del square B is equal to mu naught NS E square by M into B. We assume that mu naught ns E square by m, which is equal to 1 by del square. So this equation will become del square B is equal to 1 by lambda square B, or we can write it as del square B minus 1 by del square lambda square B is equal to 0. What is a lambda? Lambda define the London penetration depth, means up to which the magnetic field will pass through the material, and then its superconductivity will decreases. Then this is the London equation, and which define the London penetration depth for the magnetic material to define the magnetic properties of the superconductors. Now, on the basis of that, the BCS theory of superconductivity was explained. What is a BCS theory? Here we see that what is called a BCS. Now, the property of type 1 superconductors were modeled successfully by the efforts of John Bardeen, Leon Cooper and the Rutherford Schiffer. And these three scientists explain the properties of type 1 superconductors, means soft superconductors, pure superconductors, fully observe the Meissner effect, they are perfectly diamagnetism, the impurity will not change its superconductivity. Then they explain the type 1 superconductors, and these are commonly called the BCS theory. But a key conceptual element in this theory is the pairing of electron close to the Fermi level into the Cooper pair through interaction with a crystal lattice. The electrons which is very near to the Fermi level was defined by the Cooper pair, and where we define the interaction between the lattice and the electron. This pairing result form a slight attraction between the electrons related to the lattice vibration, because the electron lattice vibrations will take place. The coupling to the lattice is called a phonon interaction. When the electron interact with the lattice, then it is known as the phonon interaction. Pair of the electrons can behave very differently from single electron, which are fermions and must obey the Pauli exclusion principle. Pair of electrons can behave very differently from the single electrons, means when an level having the two electrons in its states, means they are defined differently by obeying the Fermi rules, or we can say that they must follow the Pauli exclusion principle, means two same electrons of the same symmetry will not stay in the single state. So, the pair of electrons act more like bosons, which are condensed into the same energy level. The electron pairs have a slightly low energy and leave the energy gap above them on the order of 0.001 electron volt. This is very less energy gap, which inhibits the kind of collision interactions which leads to the ordinary resistivity. For the temperature, such as the thermal energy is less than the band gap, if the thermal energy is less than the band gap difference between the two levels, conduction band and the valence band, then this material exhibits the zero resistivity. So, Bardeen, Cooper and Schiffer received the Nobel Prize in 1972 for development of the theory of superconductivity for the type 1 superconductors. What are the Cooper pairs? First we define, here the term Cooper pair was required to explain, as we know that the interaction of the electron with the lattice. Now, what is the Cooper pair? A transition of the metal from the normal to the superconducting state has the nature of condensation of the electron into a state which leaves a band gap above them. It means this type of condensation is seen with the superfluid helium, but helium is made up of boson. Means multiple electrons cannot collect into a single state because of the Pauli exclusion principle. So the electron acts as a pair coupled by the lattice vibrations in the material. It means the pairing of the electrons takes place by using the lattice vibrations in the crystal, or you can say in the material. This coupling is viewed as an exchange of photons, the coupling between the electron and the lattice, and that is exchange is viewed as a phonons, and phonon being the quanta of lattice vibration energy. This phonon is also known as the quanta of lattice vibration energy. Now, experimental of the interaction with the lattice was provided by the isotope effect on the superconducting transition material also. The boson-like behavior of such electron pairs was further investigated by the Cooper, and that's why they are called the Cooper pairs, as we are talking about the interaction between the electrons with the lattice. Now, the condensation of the Cooper pair is the foundation of BCS theory of superconductivity. Now, we see a model of the Cooper pair attraction. We see here the lattice of the superconducting material. Here we see a passing electron attracts the lattice, causing a slight ripple towards its path. Here we see another electron passing in the opposite direction is attracted to that displacement. Here we see that this is moving in the opposite direction, but the vibrations of the different lattice will take place. This is the model of pair attraction. A visual model of the Cooper pair attraction has a passing electron which attracts the lattice, causing a slight ripple towards the path. Another electron passing in the opposite direction is attracted to that displacement. This constitutes a coupling between the electrons, which can be depicted in a Feynman diagram. Here we see that this is the electron and this is the phonon which is interacting with the lattice, and this is the electron which is moving. As strange as such as interaction seems, it is experimentally supported by the isotopic effect and the evidence of the condensation to the boson-like state at a critical temperature for the superconductivity. In the normal state of the metal, electrons move independently, whereas in the BCS state, they are bound into Cooper pairs, and here we see now they will move in this manner. But if we talk about the normal state, they move freely in the material, but when it is in the Cooper pair, then they are bound by the attractive interaction. The BCS formalism is based upon the reduced potential for the electron attraction, or we can provide the energy equal to the energy gap to break the pair. To break one pair, we have to change the energies of all other pairs. This is unlike the normal metal, in which the state of an electron can be changed by adding a arbitrarily small amount of the energy. The energy gap is highest at low temperature because superconducting state, but does not exist at temperature higher than the transition temperature. So, the BCS theory gives an expression of how the gap grows within the strength of attractive interaction and the density of the state. It means this gap grows for the two material, for the two gap which with the strength of the attractive interaction between the electron and the lattice, and this will also change the density of the state of a material. The BCS theory also gives the expression of the energy gap that depends on the temperature and the critical temperature Tc and independent of the material. It means BCS theory not depend upon the condensation of the material, not depend upon the material, but it depend upon the critical temperature. So, we define here the energy E is equal to 3.52 kB Tc 1 minus T by Tc 1 by 2. It is not depend upon the material, but it is only depend upon the critical temperature. Now, we discuss about the application of superconductors in the next lecture. Thank you.
Well, just no, thank you, ma'am. Thank you so very much for giving us this session on superconductivity. Friends, if you have any queries or feedback, then do write to us at info.cec@nic.in. We are going to meet again very soon and would be discussing more. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.